I welcome you all for today's session, which is on machine independent assembler features. Our previous topic was machine dependent assembler features, where we have seen about the instruction formats and assembly directives in detail with the both SIC and also XE machine architectures. So today we'll be looking after the machine independent assembler features. Starting with the first, it is literals, then we'll be moving to the symbol defining statements, and we also look into the expressions usage in the program, and then we see the program blocks, and finally control sections and program linking at the time of object code generation and the loading process. These 5 features are considered to be machine independent assembler features. Starting with the first, literals. So before we see what is this literal, so let us have a simple example. As such, if you observe right here, this is the program code without the utilization of the literals. In this, if you observe, this is the instruction where we have LDA UOF. However, we know that this is the label part of the program, and this is the mnemonic opcode, and this is the operand. So we have the label, opcode and the operand. Now based on that, LDA is the opcode and UOF is the operand. What does it happen? What happens here? So the content of the operand should be loaded to the accumulator register. But if at all, if you want to load the content of the UOF to the accumulator register, first you should know what is the value of this UOF. Now if you want to find out the value of this UOF, so which is reference to some other memory location here, which is UOF, where the value of that UOF is UOF itself, which is the 3 characters end of file UOF, which is declared with the byte assembler directive. So what is happening here? The content of this variable UOF is the value UOF, which is fetched and will be loaded to the accumulator register in this instruction. As we know that content which is to be fetched, it is the variable which is referenced by at some other memory location, which is the UOF. So what can be done here in the sense, the content UOF, the content to be loaded to the accumulator register UOF, that can be directly assigned to the accumulator register here by using this literal operand. This literal, by using this literal, you can make use of by using this literal operand or literal constant operand, you can load the content directly to the accumulator register. So what is happening here? The content which is UOF, the 3 characters which are to be loaded to the accumulator register, can be mentioned as a operand in the instruction. So that is what the literal utilization. So here the 2 examples you can observe. So LDA is equal to COF and TD is equal to X05. Here if you observe, so what exactly this equals, in the sense, equals is the one which is to identify or represent the literals in the operand field. So remember, the literals are nothing else than the constant operands. Literals are nothing else than the constant operands which will be used as a part of the instruction itself. Which will be used as the part of the instructions itself. So which is the literal. Now here is one more example. So instead of you declare the 05 at somewhere else as a part of your output, and which will be used, which will be accessed in your program as TD output or WD output, what can be done in the sense, you can make use of the 05. You can make use of that 05, wherein 05 is the hexadecimal 05. So you can make use as X05 as a part of constant operand itself inside the instruction by using this literal operator, which is equal. So that is what the utilization of the literal. So then moving to the next, it is, so till now we saw about the literals, and here is an example. This LDA #3 and LDA is equal to COF, which somewhat looks same, but both are not same. This LDA #3, which is the immediate addressing mode instruction, and this is the LDA is equal to COF, which is a literal operand instruction. What is the major difference? In the sense that major difference you can find out from this LDA #3, as it is a direct constant value, so which doesn't need any memory referencing, it doesn't need any memory referencing, whereas in this LDA is equal to COF, even though this is the constant operand, but which do requires the memory referencing, that is the major difference you can find between the literals and the immediate addressing, which is purely based on the memory location and memory referencing. That is the major difference you can find. So in order to deal with that memory referencing with the literals, so we call that as a literal pool. As however we say literal pool, it is nothing else than the list of literals, or you say set of literals, a pool of literals. Where do you mention them? So those literals will be used at the end of the program. Basically we will be using at the end of the program as like this. So you can see right after the end instruction you will be having all the literals, whatever you used in the program, all those literals will be mentioned or will be provided at the end of the program. But is there any other possibility of using the literals in between the program? In the sense, yes, you can make use of such literals in between the program also by making use of the keyword or assembler directive. It is by using the LTORG. If you make use of this LTORG, that is what, if you make use of the assembler directive LTORG, you can make use of, or you can have the literals anywhere inside the program like this. So right after that LTORG, the next instruction will be the literal instruction or literal constant instruction. What does this LTORG? LT stands for literal and ORG stands for origin. So LTORG gives the literal origin of the particular literal. So that is how. So utilization, or you say memory referencing of the literals will be, those are the two types of memory referencing. One is at the end of the program, one is at the end of the program like this, which is just a pool of literals or a set of literals, and the second way is in between the program also you can make use of such literals or declare such kind of literals by means of this LTORG. So that is the two ways of memory referencing the literals. Then here if you think about the, just because making use of the literals in the program, does the object code varies? In the sense, as of here, let us demonstrate that. So here if you observe this LDA EOF, so it is just a format 3 instruction. However, we know that opcode of the LDA it is 00, and as it is neither immediate nor indirect, so both N and I will be 11. X, as it is not using any index register in this instruction, so X will be 0 and E will be 0. And as usual we need to find out the relative address. How to find out relative address? For PC mode it is operand address minus the PC value. Here the operand is UOF. When you find out the operand address of this UOF, operand address of the UOF it is 002D, and what is the PC value? The next address it is 001D. So 002D minus 001D will be 0010. So this is what the object code for this LDA EOF when we use as a normal symbol variable or a normal program. Now if you observe in this literal case, here again as usual opcode and flag bits will never vary. Coming to the relative address, what is this operand? Here it is a constant literal, and you do have a memory referencing. And what is that memory referencing? It is inside the same program block. We are using inside the same program block. Here is an address which is 002D, which is the operand address minus the PC value 001D. So the target address will never vary because we found it as a relative address, operand address minus the PC value. So wherein this is when you use the literal constant by making use of LTORG. If you have used the same literal by means of storing at the or having at the end of the program, then the address of that literal would be different. For example, here instead of this CEOF, instead of using here inside the program, if you have used at the end of the program here, then the address of that will be more than this 1073, anything which is more than 1073, because which is the last address of this program. So the address of that instruction would be more than 1073, and if you subtracted that 1073 by this PC value, then the object code will never be same, would be different. So that is the reason instead of having the set of literals at the end of the program itself, there is a provision to have the such kind of literals inside the program code or in between the other instructions also by using this LTORG. That is what literal origin. The next is that can we make use of the literals for many number of times in the sense? Yes. So here is an example. You declared the literal only once but used many times, which is 05 is used too many times. So you can make use of such literals many times, which is what duplicates or repeating the same literal for multiple times. Then finally coming to the lit tab. What does this lit tab in the sense? Literal table. Lit tab stands for literal table, and this lit tab is the data structure used by the used for the purpose of literals. What are all things will be available in this data structure lit tab, which is a table? In the sense, there will be 4 major fields available in the lit tab, which are what is the actual literal name, what is the operand value, and what is the operand length, and finally address. So when you talk about the literal name, per suppose what in this example again, if you take up the literal name is the COF, which is the literal name, and what is the address of that? It is this 002D. What is the value of that? It is ASCII of E, it is 45, O it is 4F, F is 46. So this is the value of the literal. And what is the length in the sense? How many bytes? It is 3 bytes. It is 3 bytes. So those are the 4 fields which are available in the lit tab, which is name, value, length, and the address. So those are the 4 fields available in the lit tab. Then what is the working of this in the sense? It works based on the hash function or hash table. It works as a hash table. You can access or use it as same as the hash table by referencing either based on literal name or based on the value. Then how do we deal with that literal table in the pass 1, pass 2 assemblers in the sense? In pass 1, you can treat this lit tab, it is as same as the sim tab for the labels. So we'll be dealing this lit tab for the literals. So you can generate the lit tab, or in the other means you can observe wherever in the program if you encounter with the LTORG, right after that statement the next program will be next instruction will be the literal instruction, and that literal instruction is to be stored to the lit tab, wherein before you need to store that to the lit tab, you have to make sure that the same kind of lit tab is not available in the lit tab already. So same kind of literal is not available in the lit tab already. So if the same kind of literal is not available in the lit tab already, then load the respective address and what is the value, length, everything to the lit tab. Then in the you will be loading the literal name and the address to the lit tab. So wherein in the pass 2 you will be accessing that address of the lit tab, which will be acting as a operand address to the other instruction. So that is to be will be used to generate the object code in the other instruction. So you will be accessing the lit tab in the pass 2 assembler for generating the object code for the other instruction. So this is all about the literals. Now let us look into the symbol defining statements. So what exactly the symbol defining statements in the sense? So till now we had used so many labels in any instruction which are purely user defined labels in the instruction, but there are the few symbols which are supported by the assembler, so which can be used repeatedly by any programmer with the help of this assembler directive. Here is one of the example, which is EQ. As the name itself specified, is for equating. It is equating. So what is how do we use this here? Here let us see this example, max length EQ 4096. However, in the earlier examples we had this as a max length word 4096. When you know that the value for the max length which you are going to assign is 4096, so you used as a max length word 4096. So we used as max length word 4096. So wherein there is a necessity of you to allocate the memory space of 3 bytes and also to store the value as 4096. Instead of that, you can also have like this as max length EQ 4096, and irrespective of either you make use of EQ or word, you can use this immediate addressing mode as plus LDT hash 4096 can also be replaced as a plus LDT max length. But what is the difference between this max length EQ 4096 and max length word 4096? In the sense, there is if you make use of this max length word 4096, there is a necessity of separate memory space which is to be pointed by this variable max length, and that will be accessed in this instruction because you are using that max length as a word as a operand here. Wherein here, in case of max length EQ 4096, there is no necessity of separate memory referencing in case of max length EQ 4096. That is a simple specialty of this EQU with respect to the any symbols, any user defined symbols. Here here max length is the user defined symbol, that the value of that max length which is defined by using this assembly directive EQU with the value 4096 instead of the word 4096. Then next, it is not only you can define for the user defined variables like this, you can also define some values, or if there is a scenario such that you don't want to use the registers in your program instructions as either it can be A or X or L or BSTF, we have PCSW as well. If you do not wanted to use them in the program like this as RMO A, X, it is a known fact that the register number of A it is 0 and the register number of X is 1. Instead of you make it as implicit, you can also make it as explicit by defining the values for those register numbers explicitly by using the EQU like this. So here is an example where you are defining the values for the registers as a 0, 1, 2 by using this EQU. So if suppose you may get that out as why can't you do it by using this word like this, in the sense at any point of time if you make use of A word 0, X word 1, L word 2, instead of this A UQ 0, X UQ 1 and L UQ 2, if you make use of A word 0, then you have X word 1 like this. If you ever do this, if you have any doubts such that why can't you make use of like this, in the sense no, at any point of time you should never make use like this, because if you even at any time if you make use like this, these X will no more be acting as a registers, they will be considered as a variables. But here we don't want them to be considered as a user variables, they are the registers which are predefined default registers which we have in AXL, BSTF and PCSW. So you can't use like this. So for that purpose you will have to make use of EQ itself. So that's one of the feature of EQU, which is equating. Then moving to forward, so here however you can initialize something with the EQ. By using EQ you can initialize to the base register, it is for initializing, and these are the two user defined variables. So you can equate anything by using the EQU either to the user defined variables like this, or it can be for the registers. That is what defined here. Now moving to the next assembly directive under this symbol defining statements, the next assembly directive which we want to highlight it is ORG. ORG, it is not organizing, it is the origin. So origin of what? Origin of the address, from where it is located. See, whenever we will be using whenever you keep incrementing the location counter to keep pointing to the further instruction, if there is a necessity to go back to the origin, to go back to the home address, so in such cases we will be using this ORG, origin. So ORG stands for origin, and this is the value to where you need to go back to the home address, origin address. Here is an example, let us see. So here is an example, there is a stab which is assigned with the 1100 bytes, whereas the address of the stab is what? 1000. So by that, so what happens here in the sense, the stab is allocated with the 1100 bytes, whereas the starting address for the stab is 1000. So whenever you keep tracking for each and every data element, whenever you have this org tab, it will be very easy to go back to the starting address, which is 1000 here. So that is the org, which is origin feature here, which is used. So then here we have the few more examples. Something if when the org is the alpha, which is defined to where you need to go back, that is what the origin, which is org. So under this symbol defining statements, you're supposed to know about the two assembler directives. One is equ, which is for equating, and the other it is org, which is for origin, which will be acting as origin. Now let us move on to the next very important concept, which is expression. Till now we have used so many parameters in the label field, and also very importantly as a operand field. But operand, whenever we made use of operand field, till now we made use as a individual variables or individual operands. But assembler supports the expressions utilization in the operand field. So what exactly is that utilizing the expression field in the sense? So when you can have by making use of this arithmetic operations, by making use of this kind of arithmetic operators, there is a possibility wherein you can make use of such kind of expressions in your instructions. As an example, if you look it here, this is what one of the example. Instead of you defined as a max length, which is equated with some other reserved value, here you can see the operand field contains an equation here. So if you observe right here, the value for this max length, you can fetch it only after if you know this buffend and buffer values. So whatever is the value of buffend and what is the value of buffer, based on that, by equating operation, based on the operation between this equation or expression, that will be assigned with the max length. So that is what we are dealing with, the expressions. Instead of you deal with the operand fields as a individual parameters, you can also have it as an equations as a operands. So inside that either you may have any kind of operators like this. It can be addition, subtraction. Here we just saw the example as subtraction like this, buffend minus buffer. So you can also have as buffend plus buffer, buffend divided by buffer, buffend multiplied by buffer. So like that, multiple variables can be put in together as a form of expression, and that expression will be acting as an operand in an instruction. So there is a possibility where our assembler supports that. But here such kind of expressions are categorized into the two cases or two types. You said as a absolute expressions and the relative addresses or relative expression. What is that absolute and the relative? It is absolute whenever it try to figure out or a resultant address, it is the absolute address or is it a relative address. Based on that, it will be classified into the two types as a absolute and the relative. For example, in till the examples we have seen till now, so in all those expressions we had, in all those instructions we have seen few as especially in case of format 3, we used to find out the relative address as, in case of PC mode we used to find as operand address minus the PC value. In case of base, we used to find out as base minus operand address minus base value. In both the cases there is a relative change. Whenever there is a change in the operand address, there will be relative change in the PC value as well. So one of the example like this, when the value of the buffend changes, definitely there will be changes in the buffer as well. So when there is if the value of the buffend and the buffer are relatively changed, when you subtract them, the resultant will never vary. So that is what one of the example as relative expression, wherein we have few are absolute expressions, something like this. When you subtract this 100 minus buffer, see the value of the buffer may change, whereas 100 will never vary. In the same way, 3 into buffer, the value of the buffer may vary, but 3 will never change. So it is as same as in this relative case. It is if I mean to say 50 minus 10, it will lead to 40. Whereas 150 minus 110 will also lead to 40 itself. So if 50, when 50 is changed to 150, here 10 is changed to the 110. So the resultant will be still 40 itself. That is what relative change. So relative expression. Wherein here, when the 100 minus buffer, when the buffer value is value is 50, the resultant is 100 minus 50 is 50. When the buffer becomes 60, 100 minus 60 is not 50, it will be 40. So the resultant will vary here as well. When 3 into buffer, when the buffer is 50, so 3 into 50 is 150. Whereas 3 into 60 is 180. So which will change. So which will acts as a absolute values. Whereas coming to this buffer and plus buffer, which may leads to neither absolute nor the relative. So based on that, here absolute and the relative expressions, there are the two cases of expressions, which is absolute expressions and the relative expressions. In the symbol table, however, we have the different fields till now, whatever you studied as what is the symbol name and what is the value, which is nothing else than the address here. So with that, we will also add up one more column, one more field here to only classify which particular symbol belongs to which type of expression, whether it is a relative expression type or is it absolute address type. So that is why in the symbol table, however you studied till now as symbol name and the symbol value address, with that there will be one more, we insert one more column into the symbol table, which is type of expression or the type of the symbol, which is it a relative symbol or is it an absolute symbol. Based on that you can have. So like that, in any instruction, you don't have to have any individual variables as operand. You can also have an expressions, and such expressions may be operated with any of the operations. The second case of the expression is something like you may also have the operand as a star like this. You may also have the star like this, wherein you may not have the complete expression. There may be the possibility of having star. What is this star in the sense? It is not multiplication star, it is something else. There is a special scenario. What exactly is that in the sense? It is this. It is the one which always the value, which is what is the value of this in the sense? It is the address of the next byte. It is the address of the next byte after the buffer area. Whenever you have a buffer area after that next byte, that is why we are equating that star with the buffer end, which is the buffer end. After the buffer, what is the next byte? That is will be fetched by this star. If the buffer space is of 100 hexadecimal bytes and the starting address is 1036, so the next address will be definitely a 2036, which will be equated to this buffer end, which is the buffer end. So understand, if the starting address is 1036 and there are the 1000 hexadecimal bytes you will be assigned to the buffer, then the next address after the end of the buffer, it is what? 2036. That is what will be the assigned with this buff end. So when do you use this star in the sense? When you doesn't know the exact size of your buffer. In such case, you do make use of this star, because the buffer content need not be constant. Every time it may be keep varying. I may store some 100 bytes into the buffer, somebody else may store some 1000 bytes into the buffer. In such scenarios, when the size of the buffer will be keep changing, in such case you can't make it constant about this buffer end, the size. Instead of calling it as size, what is the actual content of the buffer? So in such case, so we'll be using this star, which will what is the value of this in the sense? That is the address of the next byte right after the buffer end of the buffer. So which is what? Equated to the buffer end. So you can make use of the parameters like this. Otherwise, if you can also have it as a star. But whenever you make use of star, that is the one which fetches the next address after the buffer end. So that is all about the expressions. So till now we have seen about the literals and symbol defining statements in that EQ and the ORG, and we saw a few things about the expressions. So